Hello there, and welcome to the Sleepy Library. It's lovely to have you here. Before we begin, I'd love to know where in the world you are listening from tonight. A peaceful bedroom, a quiet corner of your home, perhaps beneath warm blankets as the day comes to a gentle close. Wherever you are, I hope you're comfortable, safe, and ready to embark on a soft journey through the cosmos. If you enjoy these soothing explorations and would like to hear more, a like and subscribe really helps this small channel continue to float along among the stars. And to those of you already subscribed, thank you. Truly, your support means more than you know. Tonight, we'll be exploring something rather wonderful: strange objects in the solar system. Not the familiar planets and moons you've known since childhood, but the peculiar, the unexpected, the mysterious. We'll visit worlds that spin so fast they've stretched themselves into footballs, moons with surfaces that look like someone assembled them from mismatched puzzle pieces, and wanderers from beyond our solar family that have come to visit us from the depths of interstellar space. I'll try not to make these mysteries so captivating that they keep you awake. But if they do, at least you'll have learned about some of the most fascinating corners of our cosmic neighborhood. A small price to pay for a curious mind. So settle in, let your breathing slow, and let's begin this gentle voyage through the remarkable and the strange. The solar system, at first glance, seems orderly. 8 planets marching in their orbits around the Sun, moons attending their parent worlds like dutiful companions, asteroids clustered in a belt between Mars and Jupiter. It's a picture of cosmic organization, a celestial clockwork that runs with predictable precision. But look closer, just a bit closer, and you'll find that our solar neighborhood is filled with oddities. With objects that don't quite fit the pattern, with worlds that challenge our expectations at every turn. These strange objects tell us something important. They remind us that the universe doesn't always follow the rules we expect. They show us that planetary formation, the grand process that built our solar system 4.5 billion years ago, was far messier and more chaotic than we sometimes imagine. And they offer us glimpses into processes and phenomena that exist nowhere else we've yet discovered. Tonight, we'll meet some of these cosmic oddities. We'll travel to the outer reaches of the solar system and beyond. We'll examine surfaces scarred by ancient impacts and shaped by forces we're only beginning to understand. We'll ponder mysteries that scientists are still working to solve. And through it all, we'll move slowly, gently, letting each strange world reveal its secrets at a pace that invites rest rather than excitement. So close your eyes if you wish. Let your mind wander among these distant realms. And let's begin with a visitor from another star, On. A quiet night in October of the year 2017. A telescope on the island of Hawaii spotted something unusual. It was moving across the sky, but its path was wrong, all wrong. When astronomers calculated its trajectory, they realized they were witnessing something unprecedented. This object wasn't orbiting the Sun like everything else in our solar system. It was passing through, traveling so fast that the Sun's gravity couldn't capture it. It had come from somewhere else, from the vast spaces between the stars, and it was only here for a brief visit before heading back out into the cosmic ocean. They named it Oumuamua, a Hawaiian word meaning scout or messenger, the first emissary arriving from afar. And what a strange messenger it was. As telescopes around the world turned to observe it, Each new measurement added another layer of mystery. The object was small, somewhere between 100 and 400 meters long, tumbling end over end as it raced through our solar system. Its brightness varied dramatically as it rotated, suggesting a highly unusual shape. Where most asteroids and comets are relatively round, or perhaps slightly elongated, Oumuamua appeared to be extremely elongated, perhaps 10 times longer than it was wide. Imagine a cosmic cigar, or perhaps a flat pancake, spinning through space. No asteroid or comet in our solar system has such an extreme shape. The color was strange too. Oumuamua had a reddish hue, similar to objects in the outer solar system that have been exposed to cosmic radiation for billions of years. This suggested great age, a traveler that had been wandering between the stars for an immensely long time. Scientists estimated it had been traveling through interstellar space for hundreds of millions of years before its chance encounter with our Sun. During all that time, it had been bathed in cosmic rays, high-energy particles that slowly altered its surface, giving it that distinctive reddish color. But the strangest thing about Oumuamua was what it didn't do. When comets approach the Sun, they warm up. Ice on their surface begins to vaporize, creating the characteristic tail that makes comets so beautiful in our night skies. The escaping gas also gives comets a little push, a rocket effect that slightly alters their trajectory. Scientists expected to see something similar with Oumuamua, but there was no tail, no visible coma of gas and dust surrounding the object. And yet, as they tracked it, they noticed that Oumuamua was accelerating slightly, receiving that characteristic push away from the Sun. Something was giving it that push, but they couldn't see what. This mystery sparked intense debate. If there was no visible outgassing, what was causing the acceleration? Some scientists proposed that Oumuamua might be made of solid nitrogen ice, similar to the surface of Pluto. Nitrogen sublimates at cold temperatures, turning from solid to gas without becoming liquid first, and it's harder to see than water vapor. Perhaps Oumuamua was a fragment knocked off from a Pluto-like world in another solar system billions of years ago, now slowly evaporating as it passed near our Sun. The elongated shape could be explained by this process too, like a bar of soap gradually wearing away as its outer layers sublime into space. Others proposed even more exotic explanations. What if Oumuamua was incredibly porous, like a cosmic dust bunny, so loosely bound together that it was mostly empty space? Or what if it was made of hydrogen ice, frozen hydrogen that would sublimate invisibly as it warmed? Each hypothesis tried to explain the observations, to make sense of this strange visitor. By January of 2018, Oumuamua had passed beyond the reach of our telescopes, heading back out into interstellar space. It's now racing away from the Sun at about 26 kilometers per second, heading roughly toward the constellation Pegasus. In about 20,000 years, it will be as far from the Sun as Proxima Centauri, the nearest star to our own, and we'll never see it again. But Oumuamua taught us something important. It taught us that our solar system is not isolated. There are objects out there, countless objects probably, drifting between the stars. These are the fragments of other solar systems, pieces knocked loose by impacts or gravitational interactions, now wandering the galaxy on their own. Oumuamua was the first such interstellar visitor we detected, but it won't be the last. Already, astronomers have spotted two more. In 2019, a comet named Borisov was discovered, clearly interstellar in origin. And more recently, in 2025, another visitor called 3-Eye Atlas was detected. As our telescopes improve, we'll undoubtedly spot more of these cosmic travelers, each one offering us a glimpse of distant planetary systems we may never visit. Rest easy, knowing that these interstellar visitors pose no threat. They're too small and too far away. They simply pass through, cosmic postcards from distant realms, before continuing their lonely journeys through the void. Let's move now from visitors to our solar system to permanent residents that are equally strange. Let's journey out to the Kuiper Belt, that vast region of icy bodies beyond Neptune, where dwarf planets tumble in the cold and dark. Far beyond Neptune, in the frozen outer reaches of the solar system, orbits a world unlike any other. It's called Haumea, named after the Hawaiian goddess of childbirth and fertility, and it's one of the strangest objects we've ever discovered. If you could see Haumea with your own eyes, it would look wrong, fundamentally wrong, because it's not round. Where most large objects in space are spherical, pulled into roundness by their own gravity, Haumea is shaped like an American football, stretched out along one axis. Its longest dimension is about 2,300 kilometers, but its shortest is only about 1,100 kilometers. It's been squashed and stretched into an ellipsoid, a cosmic egg tumbling through space. The reason for this extraordinary shape is speed. Haumea spins faster than any other large object in the solar system. A day on Haumea lasts only 4 hours. That's how long it takes to complete one rotation. This furious spin creates centrifugal force that pulls material away from its poles and out toward its equator, stretching the dwarf planet into its football shape. Imagine spinning a ball of clay on a pottery wheel, faster and faster, watching it flatten and spread. That's essentially what's happened to Haumea, though on a planetary scale. But why is Haumea spinning so fast? The answer, scientists believe, lies in its violent past. Billions of years ago, Haumea was probably a more typical round object, similar to Pluto. Then something catastrophic happened. Another large object, perhaps half the size of Haumea itself, smashed into it at tremendous speed. The impact was devastating. It stripped away much of Haumea's icy mantle, leaving behind a rocky core covered by only a thin shell of ice. It sent fragments flying in all directions, and it set Haumea spinning like a cosmic top, a rotation that continues to this day. Some of those fragments became Haumea's 2 moons, Hi'iaka and Namaka, named after daughters of the Hawaiian goddess. Other fragments went into orbit around the Sun themselves, becoming smaller Kuiper Belt objects that share Haumea's unusual characteristics. They all have high water ice content and similar orbital properties, a family of objects all born from that ancient collision. The impact explains another mystery about Haumea. Its surface is remarkably bright, reflecting about 51% of the sunlight that hits it. This is unusual for objects so far from the Sun, which tend to accumulate dark organic compounds on their surfaces over billions of years. But Haumea's surface appears to be freshwater ice, perhaps exposed by the ancient impact that stripped away its outer layers. There's also a dark red spot on the surface, possibly an impact crater that has revealed some of the mineral-rich material beneath the ice. In 2017, astronomers made another surprising discovery. Using 12 telescopes at 10 different observatories across Europe, they watched as Haumea passed in front of a distant star. This technique, called stellar occultation, is remarkably useful. By watching how the star's light dims and changes as Haumea passes in front of it, astronomers can determine the object's exact size, shape, and even detect features around it. What they found astonished them. Haumea has rings. A thin ring of material, about 70 kilometers wide, orbits the dwarf planet at a distance of about 2,287 kilometers from its center. The ring lies in the same plane as Haumea's equator and the orbit of its larger moon, Hi'iaka. This was remarkable for several reasons. Haumea became the first dwarf planet and the first Kuiper belt object known to have rings. Previously, rings had only been found around giant planets like Saturn and Jupiter, and around a few much smaller objects called centaurs that orbit between Saturn and Uranus. The discovery suggested that rings might be more common in the solar system than previously thought. They might even be a natural consequence of certain types of impacts or tidal interactions. The particles in Haumea's ring appear to be in a special orbital resonance with the dwarf planet's rotation. They complete one orbit for every 3 times Haumea spins. This 3-to-1 resonance might help keep the ring stable, preventing the particles from either falling onto Haumea or escaping into space. The origin of the ring is probably connected to the same ancient impact that shaped Haumea and created its moons. Perhaps some of the debris from that collision settled into a ring around the dwarf planet, or perhaps one of Haumea's moons later broke apart, either from another impact or from tidal forces, creating the ring we see today. Whatever its origin, the ring adds to Haumea's already impressive list of unusual features. A football-shaped dwarf planet spinning once every 4 hours with 2 moons and a ring system. It's a cosmic oddity, a reminder that even in the cold, dark reaches of the outer solar system, strange and wonderful things can happen. Let the image of Haumea spinning in the darkness rest gently in your mind. A distant world, far from the warmth of the sun, marked by ancient violence, yet beautiful in its strangeness. Let's continue our journey inward now, towards Saturn, where we'll encounter a moon that has puzzled astronomers for more than 3 centuries. When the Italian-French astronomer Giovanni Cassini discovered Saturn's moon Iapetus in October of 1671, he immediately noticed something peculiar. The moon appeared bright when it was on one side of Saturn, but when it moved to the other side, it became so dim he could barely see it, even with his best telescope. Cassini puzzled over this for years before reaching a conclusion that remarkably turned out to be correct. He proposed that Iapetus must have 2 very different hemispheres. One side, he suggested, was bright and icy, while the other was extraordinarily dark. And because Iapetus is tidally locked, always showing the same face to Saturn as it orbits, observers on Earth would alternately see the bright hemisphere and the dark one as the moon circled its planet. For centuries, Iapetus remained mysterious, a distant enigma visible only as a point of light that varied in brightness. It wasn't until spacecraft visited Saturn that we could see Iapetus clearly, and the reality exceeded even Cassini's prescient observations. The moon is indeed 2-toned, startlingly so. One hemisphere is as white as fresh snow, reflecting about 60% of the sunlight strikes it. The other hemisphere is as black as asphalt, absorbing most of the light and reflecting only about 4 or 5%. The contrast is so stark that Iapetus looks like it's been dipped halfway in tar. Where the 2 regions meet, the boundary is surprisingly sharp, not a gradual transition, but an abrupt change from bright to dark. The dark region, named Cassini Regio in honor of the moon's discoverer, covers most of the leading hemisphere, the side that faces forward as Iapetus orbits Saturn. The bright region, called Roncevaux-Terra, dominates the trailing hemisphere. But what could create such a dramatic difference? For years, scientists debated whether Iapetus was a bright moon with a dark coating or a dark moon with bright patches. The answer, it turns out, involves a complex process that starts far from Iapetus itself. Beyond Iapetus's orbit, even farther from Saturn, circles another moon called Phoebe. Phoebe is unusual too. Unlike most of Saturn's moons, which orbit in the same direction as the planet rotates, Phoebe orbits backward, in what's called a retrograde orbit. This suggests that Phoebe wasn't formed along with Saturn like the other moons, but was instead captured, an interloper that wandered too close to Saturn's gravity and became trapped in orbit. Phoebe's surface is dark, covered in primitive material left over from the formation of the solar system. As Phoebe orbits, it slowly loses material from its surface. Micrometeorite impacts knock particles loose. The weak warmth of the distant sun causes some ices to sublime, releasing dust particles. Over millions of years, this creates a vast, diffuse ring of dark material in Phoebe's orbit and beyond. Astronomers discovered this ring in 2009 using the Spitzer Space Telescope. It's enormous, starting about 6 million kilometers from Saturn and extending outward for another 6 million kilometers or more. It's also incredibly tenuous, so thin and sparse that you could fly through it without noticing. But over millions of years, even this tenuous material can have an effect. As Iapetus orbits Saturn, it plows through this ring of dark material. The particles accumulate on its leading hemisphere, the side that faces forward in the direction of motion, like bugs hitting a windshield. Slowly, gradually, a coating of dark material builds up on that hemisphere. But that's only part of the story. The dark coating doesn't just darken the surface, it also changes its temperature. Dark surfaces absorb more heat from the sun than bright surfaces do. So as the dark coating builds up, that hemisphere of Iapetus becomes warmer, perhaps 15 degrees Celsius warmer than the bright hemisphere. This might not sound like much, but it's enough to trigger a feedback process that amplifies the effect. Even far from the sun, water ice on Iapetus's surface can slowly sublime, turning directly from ice to water vapor, especially on the warmer, darker side. The water vapor molecules drift away from the warm hemisphere and eventually settle on the colder, brighter hemisphere, where they freeze again. Over millions of years, this process transports water ice from the dark side to the bright side, making the dark regions even darker as the ice is removed and the underlying dark material is exposed, and making the bright regions even brighter as they accumulate fresh ice. It's a runaway process. Once it starts, it reinforces itself, creating the stark contrast we see today. But Iapetus has another mystery, one even stranger than its two-toned coloring. Running along its equator, circling more than 3/4 of the way around the moon, is an enormous ridge. This equatorial ridge is about 1,300 kilometers long, 20 kilometers wide, and in places rises more than 13 kilometers above the surrounding surface. Some peaks along the ridge reach 20 kilometers high. To put this in perspective, Mount Everest on Earth is about 9 kilometers high. The ridge is so large that it gives Iapetus a distinct walnut-like appearance, as if someone had glued two halves of a sphere together and left a seam running around the middle. The origin of this ridge remains mysterious. Several theories have been proposed, but none completely explains all of its features. Some scientists suggest that the ridge formed early in Iapetus's history, when the Moon was rotating much faster than it does today. The rapid rotation would have caused Iapetus to bulge at its equator. Later, as tidal forces from Saturn slowed Iapetus's rotation, the bulge froze in place, leaving the ridge we see today. But this theory has problems. The calculations suggest that Iapetus would have needed to rotate once every 16 hours to create such a pronounced equatorial bulge, and there's no clear evidence it ever rotated that fast. Another theory proposes that the ridge is the remains of a ring system that once orbited Iapetus. Perhaps early in its history, Iapetus had its own ring, similar to Saturn's but much smaller. Over time, gravitational interactions could have caused the ring particles to spiral inward, eventually crashing onto Iapetus's equator and building up the ridge we see today. This is an intriguing idea, but it raises new questions. How would Iapetus have acquired a ring in the first place? And why would all the material fall precisely at the equator? Yet another theory suggests that the ridge formed from volcanic activity early in Iapetus's history. Material from the Moon's interior could have welled up along a line of weakness at the equator, creating the ridge. But this seems unlikely, given Iapetus's small size and cold temperatures. Such a small moon would have cooled quickly, and it's hard to see how it could have remained geologically active long enough to build such a massive structure. Most recently, some scientists have proposed that the ridge might be the remnant of a moon that once orbited Iapetus. This subsatellite would have been gradually pulled closer by tidal forces until it came within Iapetus's Roche limit, the distance at which tidal forces become strong enough to tear an object apart. The destroyed moon would have formed a debris ring around Iapetus, which then rained down onto the equator, building the ridge. This theory has the advantage of explaining why the ridge sits precisely on the equator, and why it appears to be made of the same material as the rest of Iapetus. But it requires Iapetus to once have had a second moon, and there's no independent evidence for this. The truth is, we don't know for certain how Iapetus's equatorial ridge formed. It remains one of the great unsolved mysteries of the solar system, a feature that is unique among all known worlds. Perhaps future missions to Saturn will help solve this puzzle, giving us higher resolution images and more detailed measurements. Until then, the ridge stands as a testament to the strange and unpredictable processes that shape worlds in our solar system. Iapetus itself is a moon of contrasts and mysteries, half bright as snow, half dark as coal, with a seam running around its middle like cosmic stitching. It's been called the yin and yang of the solar system, and it's one of the most visually striking objects humans have ever seen in space. Close your eyes now and picture it. A sphere half bright, half dark, with that mysterious ridge running along its equator. It's an image that will linger in your mind as you drift towards sleep. Let's journey now to an even smaller moon, one that looks like it was assembled by accident, as if pieces from different worlds were haphazardly glued together to create something unique and strange. Let's visit Miranda, the smallest and innermost of Uranus's 5 major moons, and perhaps the most geologically bizarre object in the entire solar system. Miranda was discovered in February of 1948 by the Dutch-American astronomer Gerard Kuiper. It appeared as a tiny point of light in photographs of Uranus taken at the McDonald Observatory in Texas. For nearly 40 years, that's all it was. A distant speck about which we knew almost nothing except its orbit. Then, in January of 1986, NASA's Voyager 2 spacecraft swept past Uranus, and everything changed. Because of the trajectory Voyager 2 needed to take to reach Neptune, its next destination, the spacecraft passed remarkably close to Miranda, closer than to any other Uranian moon. What the spacecraft's cameras revealed astonished everyone. Miranda's surface was unlike anything seen before in the solar system. It looked as though several completely different landscapes had been cut out of different worlds and randomly assembled into a single moon, like a patchwork quilt made from mismatched pieces. There were ancient, heavily cratered highlands, reminiscent of our own moon's highlands. There were smooth, younger plains with relatively few craters. And most remarkably, there were three enormous features that scientists called coronae, strange, grooved, ridge and valley regions that looked like nothing else in the solar system. The coronae, named Inverness, Arden, and Elsinore, after locations in Shakespeare's plays, are Miranda's most distinctive features. They appear as large, oval, or trapezoidal areas on the surface, marked by parallel ridges and grooves that give them a corrugated appearance. The ridges can be several hundred meters high and stretch for hundreds of kilometers. The coronae are separated from the surrounding, more heavily cratered terrain by sharp boundaries, like ill-fitting pieces in a jigsaw puzzle. It's these sharp boundaries that make Miranda look assembled. There's no gradual transition between the different terrains. Instead, ancient cratered surfaces abruptly give way to younger grooved regions, as if someone had cut out sections of different surfaces and glued them together. But perhaps even more dramatic than the coronae are Miranda's cliffs. The moon is crossed by enormous fault scarps, towering cliff faces that dwarf anything on Earth. The most famous is Verona Rupes, named after the city in Shakespeare's Romeo and Juliet. This cliff face rises between 5 and 20 kilometers high, depending on which measurements you trust, making it the tallest known cliff in the solar system. The height is difficult to fathom. Earth's Grand Canyon, by comparison, is only about 1.8 kilometers deep. Verona Rupes is more than 10 times taller. What makes these cliffs even more extraordinary is Miranda's gravity. The moon is small, only about 470 kilometers in diameter, with a surface gravity less than 1% of Earth's. A person standing at the top of Verona Rupes would weigh less than a kilogram. If you dropped a rock off the edge, it would fall for about 10 to 12 minutes before hitting the bottom, gently accelerating in the weak gravity. This has led to amusing speculation. Miranda might be the only place in the solar system where you could survive jumping off a 20-kilometer cliff, provided you had some way to slow your fall before hitting the bottom. A jetpack, perhaps, since Miranda has no atmosphere and parachutes wouldn't work. But what created Miranda's bizarre surface? Why does such a small moon show evidence of such intense geological activity? Several theories have been proposed. The most dramatic suggests that Miranda was literally shattered by a massive impact sometime in its past. The collision broke the moon into pieces, which then gradually reaccumulated under their own gravity. This would explain the patchwork appearance. Different fragments from different parts of Miranda's interior would have been exposed, each with its own geological history, and they would have reassembled in a somewhat random fashion. However, this catastrophic theory has fallen out of favor. The more scientists study Miranda, the less likely it seems that the moon was completely destroyed and reassembled. The problem is that if Miranda had been shattered, we'd expect to see more evidence of the impact and reassembly. The different terrains would be even more randomly distributed. Instead, the coronae show evidence of organized geological processes, suggesting they formed in place, rather than being fragments from a shattered moon. A more likely explanation involves tidal heating. Uranus has several moons, and their gravitational interactions with each other can create orbital resonances. situations where the moon's orbital periods have simple mathematical relationships. When moons are in such resonances, they tug on each other in rhythmic patterns, and these gravitational tugs can flex the moon's interiors, generating heat through friction. Scientists believe that Miranda was once in an orbital resonance with Umbriel, another of Uranus's moons. The resonance would have caused Miranda's interior to heat up, perhaps enough to partially melt. This internal heat could have driven geological activity, causing material from the interior to rise toward the surface and creating the coronae we see today. The tidal heating would have caused Miranda's icy crust to stretch and crack, forming the enormous cliffs. Different areas heated at different rates, explaining why some regions appear much younger than others. Eventually, the orbital resonance ended, perhaps through chaotic interactions with other moons. Miranda's orbit changed, the tidal heating stopped, and the moon froze in its current state, its bizarre surface preserved for us to see millions of years later. What makes Miranda's geological activity so surprising is its size. Small moons usually cool quickly and become geologically inactive. They simply don't have enough internal heat to drive processes like volcanism or tectonics. Yet Miranda, despite being one of the smallest roughly spherical objects in the solar system, shows clear evidence of recent and intense geological activity. The coronae appear to be only a few 100 million years old in some areas, quite young by solar system standards. This suggests that whatever processes shaped Miranda continued much longer than anyone expected. Voyager 2's images of Miranda remain the only close-up photographs we have. The spacecraft's flyby was brief, lasting only a few hours, and it could only photograph the southern hemisphere because that was the side facing the sun during the encounter. The northern hemisphere remains unseen, a mystery. Perhaps it's even stranger than what we've already observed. Perhaps it's similar. We won't know until another spacecraft visits Uranus. There's something wonderfully strange about Miranda. It's a small, cold world that should be geologically boring, yet it has some of the most dramatic terrain in the entire solar system. It's a reminder that we shouldn't judge celestial bodies by their size. Even tiny moons can harbor mysteries and surprises. Even distant frozen worlds can be places of extraordinary geological drama. Let the image of Miranda rest in your thoughts. A small moon with towering cliffs and mismatched terrains, orbiting a planet that itself lies on its side, far from the warmth of the sun. It's a world that seems to defy our expectations at every turn. Let's move on now from these individual strange worlds to discuss entire regions of the solar system that are revealing themselves to be far more complex and mysterious than we once believed. Let's journey to the Kuiper Belt, that vast realm of icy objects beyond Neptune's orbit, where new discoveries are changing our understanding of the outer solar system. The Kuiper Belt is a donut-shaped region of space that extends from about 30 astronomical units from the Sun, just beyond Neptune's orbit, to perhaps 50 or even 60 astronomical units outward. An astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So we're talking about a region that begins about 4.5 billion kilometers from the Sun and extends outward for another 3 billion kilometers or more. It's a vast, cold realm, far from the Sun's warmth, where temperatures hover around -220 degrees Celsius. For decades, astronomers thought the Kuiper Belt was relatively simple. It was known to contain thousands of icy objects, small worlds left over from the formation of the solar system. Pluto is the most famous resident, along with other dwarf planets like Eris, Makemake, and Haumea. The belt was thought to have a relatively sharp outer edge, around 50 astronomical units, beyond which the number of objects dropped dramatically. But recent observations are changing this picture, revealing that the Kuiper Belt is more complex and mysterious than we imagined. Starting around 2021, astronomers using the powerful Subaru telescope in Hawaii began a systematic search for Kuiper Belt objects. They were looking for potential targets for NASA's New Horizons spacecraft, which had visited Pluto in 2015, and a Kuiper Belt object called Arrokoth in 2019. The spacecraft was continuing outward, and scientists hoped to find another object it could visit. To find suitable targets, they needed to search a difficult region of the sky, one that appeared very close to the bright center of the Milky Way, making faint objects hard to spot. What they found surprised them. Among the expected objects orbiting between 30 and 50 astronomical units, they discovered about a dozen objects much farther out, orbiting beyond 60 astronomical units. This was unexpected. The Kuiper Belt was supposed to end around 50 AU. Yet, here were objects nearly twice as far away, well beyond what should be the belt's outer edge. At first, scientists were cautious. With such a small sample, it was hard to know if these were just a few unusual objects, or if they represented a larger population. But as they continued searching and analyzing old data, the evidence mounted. There appeared to be a second population of Kuiper Belt objects in the outer regions. Supporting evidence came from an unexpected source. The New Horizons spacecraft itself has a dust counter, an instrument that measures the number of tiny dust particles that impact the spacecraft. In the Kuiper Belt, dust is created when objects collide with each other, grinding slowly against each other over millions of years. Scientists expected the dust counts to drop sharply after New Horizons left the main Kuiper Belt around 50 AU. Instead, the dust counts remained steady. There was still material out there, beyond the supposed edge of the belt. Then, in late 2024, researchers analyzing the orbits of known Kuiper Belt objects made another surprising discovery. Using machine learning algorithms to search for patterns in the data, they found evidence for a hidden structure, something they called an inner kernel. The Kuiper Belt already had a known clump of objects at about 44 AU, but the new analysis suggested there was another clump, an inner kernel, at about 43 AU. What made this structure interesting was how calm it appeared. The objects in this inner kernel have very circular orbits that lie close to the plane of the solar system. They're not eccentric or tilted like many other Kuiper Belt objects. This suggests the inner kernel is old, a structure that has remained largely undisturbed for billions of years. The existence of this inner kernel might provide clues about the early history of the solar system. Current theories suggest that the giant planets, Jupiter, Saturn, Uranus, and Neptune, didn't form in their current positions. Instead, they migrated inward and outward through gravitational interactions with the surrounding disk of planetary material. Neptune, in particular, is thought to have formed closer to the Sun and migrated outward to its current position. As Neptune migrated, it would have gravitationally scattered many objects, either ejecting them from the solar system entirely or pushing them into more distant orbits. But some objects would have been captured temporarily, held in gravitational resonances with Neptune before being released again. The inner kernel might be a remnant of this process. Objects caught in Neptune's gravitational influence during its migration would have been stirred up, their orbits circularized. When they were released, some settled into the calm, circular orbits we see today. By studying the inner kernel, scientists hope to learn more about how Neptune migrated and how the outer solar system reached its current configuration. It's like reading a fossil record, except instead of bones buried in rock, we're looking at orbital patterns frozen in the structure of the Kuiper belt. These discoveries suggest that the Kuiper belt is larger and more complex than we thought. Perhaps it doesn't end abruptly at 50 AU. Perhaps it extends outward in a more gradual fashion, or perhaps there are multiple populations of objects at different distances. As our telescopes improve, we'll undoubtedly discover more objects and more structures hidden in the outer solar system. The Vera C. Rubin Observatory in Chile, which began operations recently, is expected to discover about 40,000 new Kuiper belt objects in the coming years. Each discovery will add to our understanding of this distant region. The Kuiper belt is important because it preserves material from the earliest days of the solar system. These icy objects formed 4.5 billion years ago and haven't changed much since. Unlike the inner planets, which melted and differentiated, with heavy elements sinking to their cores and light materials rising to their surfaces, Kuiper belt objects remain largely pristine. They're fossils, samples of the original material from which the solar system formed. By studying them, we can learn about the conditions in the early solar system, about the chemical composition of the primordial cloud from which we emerged. Some Kuiper belt objects have characteristics that are truly unusual. Arrokoth, the object New Horizons visited in 2019, has a bizarre shape. It looks like two flattened spheres gently joined together, a cosmic snowman painted reddish by eons of exposure to cosmic radiation. Close examination of Arrokoth's surface revealed strange mounds on its larger lobe, regular features that appear to be the remnants of smaller objects that gently merge together to form Arrokoth. It's one of the few objects where we can see direct evidence of the accretion process, the gentle collision and merging that built larger objects from smaller ones in the early solar system. Another strange Kuiper belt object is 2001 QW322, a binary system consisting of two objects of almost exactly the same size orbiting each other. What makes this binary unusual is the distance between the two objects. They orbit about 125,000 kilometers apart, taking 25 to 30 years to complete one orbit around each other. For such small objects, this is an enormous separation. Scientists believe this binary has remained essentially unchanged for about 1 billion years, a remarkably stable arrangement that preserves conditions from the early solar system. Then there's Sedna, an object so distant and with such an unusual orbit that it doesn't quite fit into any category. Sedna's orbit is extremely elongated. At its closest approach to the Sun, it comes within about 76 AU, but at its farthest point, it retreats to about 937 AU, far beyond the Kuiper belt, far beyond anything else we've catalogued. It takes more than 10,000 years to complete one orbit. Sedna never comes close enough to Neptune to be gravitationally perturbed by that. Planet, so it's not part of a population called the scattered disk, objects whose orbits were altered by Neptune's gravity. Instead, Sedna appears to be part of a different population entirely, perhaps objects that formed in place at great distances, or perhaps objects whose orbits were altered by a passing star billions of years ago when the Sun was still part of its birth cluster. The existence of objects like Sedna, and potentially many others we haven't yet discovered, raises intriguing questions. If there are objects with such extreme orbits, what else might be out there? Could there be larger objects, perhaps even a massive planet, orbiting in the distant reaches of the solar system? This brings us to one of modern astronomy's most intriguing mysteries, the hypothetical Planet 9. In 2016, two astronomers, Mike Brown and Konstantin Batygin, published a paper arguing that the orbits of several distant objects in the outer solar system showed a peculiar pattern. Their orbits were clustered, all tilted in roughly the same direction, as if something massive was gravitationally shepherding them. The simplest explanation, Brown and Batagian argued, was an undiscovered planet, a world perhaps 7 times more massive than Earth, orbiting somewhere between 200 and 1000 AU from the Sun. If Planet 9 exists, it would be incredibly difficult to find. At such great distances, it would reflect very little sunlight, appearing as a faint point of light even in our most powerful telescopes. Its orbital period would be enormous, perhaps 10,000 to 20,000 years, meaning it moves very slowly across the sky. Despite several extensive searches, Planet 9 has not been found. Some astronomers remain skeptical, suggesting that the clustering of orbits might be due to observational bias rather than a real planet. Others point out that similar orbital clustering has been seen around other stars, suggesting it might be a natural consequence of planetary system formation. Whether or not Planet 9 exists, the search for it has led to many other discoveries. Each survey designed to find this hypothetical world catalogues thousands of other objects, building our understanding of the outer solar system. And the debate itself is valuable, pushing astronomers to think carefully about what we know and what we don't know about the distant reaches of our cosmic neighborhood. Perhaps Planet 9 will be found tomorrow. Perhaps it doesn't exist at all. Either answer will teach us something important about our solar system and how it formed. Take a moment now to picture the outer solar system. Vast distances, dark and cold. Thousands of icy worlds tumbling through the void, most too small and distant to ever be seen clearly. Strange structures hidden in their orbital patterns. Perhaps even a massive planet lurking in the darkness, waiting to be discovered. It's a frontier, a realm we're only beginning to explore. Let's return, now to closer regions, to Saturn's magnificent system of moons, where we'll encounter a few more oddities that deserve our attention. We've already visited Iapetus, but Saturn has other strange moons worth exploring. Consider Hyperion, one of the most unusual moons in the entire solar system. Hyperion is potato-shaped, or perhaps more accurately, sponge-shaped. It's about 360 kilometers across at its longest dimension, but it's not round, and it's not even a regular ellipsoid. Instead, it's highly irregular, a lumpy, cratered object that tumbles chaotically through space. Most moons are tidally locked, always showing the same face to their parent planet, just as our moon always shows us the same face. But Hyperion is in chaotic rotation. Its orientation changes unpredictably over time because its irregular shape and its orbit make its rotation inherently unstable. If you were standing on Hyperion, you would see Saturn moving unpredictably across the sky, rising and setting at irregular intervals. The moon's rotation is truly chaotic in the mathematical sense, meaning that tiny changes in initial conditions lead to vastly different outcomes. You cannot predict how Hyperion will be oriented a few months from now, except in a statistical sense. Hyperion's surface is also strange. It's covered with deep, sharp-edged craters that give it a spongy appearance, like a cosmic bath sponge or a piece of pumice stone. The craters don't have the usual rounded bowl shape. Instead, they're flat-bottomed with steep walls, suggesting that Hyperion has very low density and is extremely porous. It might be more empty space than solid material, held together weakly by gravity. This would also explain why the craters are so well preserved. On a denser object, crater walls would gradually slump over time, but on porous Hyperion, they remain sharp and distinct. The Cassini spacecraft discovered another peculiarity about Hyperion. The moon appears to be electrically charged, When Cassini flew past, it detected a beam of electrons flowing away from the Moon's surface. The low-density surface material, constantly bombarded by particles from Saturn's magnetosphere, has built up a static charge. Hyperion is essentially a giant celestial capacitor, slowly accumulating and releasing electrical charge as it tumbles through space. If you could touch Hyperion's surface, you might get a shock. Saturn has another strange moon called Enceladus. It's a small, icy world, only about 500 kilometers in diameter, smaller than many other moons in the Saturn system. You would expect such a small moon to be geologically inactive, frozen solid, cratered and unchanging. Instead, Enceladus is one of the most geologically active bodies in the entire solar system. From its south polar region, enormous geysers of water vapor and ice particles spray into space, creating a plume that rises hundreds of kilometers above the surface. The Cassini spacecraft flew through these plumes multiple times, analyzing their composition. The plumes contain water vapor, salt, organic compounds, and even molecular hydrogen, all materials that suggest Enceladus has a liquid water ocean beneath its icy crust. The geysers come from 4 long fractures near the South Pole, nicknamed tiger stripes because of their distinctive appearance. These fractures are warmer than their surroundings, perhaps as much as 100 Kelvin warmer, which in the frigid outer solar system means they might be near the freezing point of water. Somehow, despite Enceladus's small size, its interior is being heated, keeping an ocean liquid and driving the geysers we see. The heat probably comes from tidal forces. Enceladus is in an orbital resonance with another moon, Dione, and this resonance causes tidal flexing that generates heat through friction. The discovery of Enceladus's ocean and geysers is one of the most important findings in planetary science in recent decades. Here is a place with liquid water, organic compounds, and an energy source, the basic ingredients for life as we know it. Scientists now consider Enceladus one of the most promising places to search for extraterrestrial life in our solar system. Perhaps microbial life exists in that hidden ocean. Perhaps the geysers occasionally carry evidence of that life into space, where we could sample it. Future missions to Enceladus will undoubtedly try to answer these questions. Jupiter's moon Io is strange in a different way. It's the most volcanically active body in the entire solar system. Its surface is constantly being resurfaced by volcanic eruptions, making Io perpetually young. There are no impact craters on Io because they're all buried under fresh lava within a few million years. The volcanism is driven by tidal heating, similar to what we discussed with Miranda, but far more intense. Io is caught between Jupiter's immense gravity and the gravitational tugs of the other Galilean moons, Europa, Ganymede, and Callisto. These competing forces flex Io's interior, generating enormous heat. The result is a world with hundreds of active volcanoes, some of which produce eruption plumes that rise 300 kilometers above the surface. Io's volcanoes are unlike Earth's volcanoes. Many of them erupt sulfur and sulfur dioxide rather than silicate lava. The erupting material is often much hotter than Earth's lava, reaching temperatures of 1,400 degrees Celsius or more. The eruptions create vast lava lakes, towering mountains, and bizarre surface patterns. Io is painted in yellows, oranges, reds, and blacks from the various forms of sulfur and sulfur compounds that cover its surface. It looks like a cosmic pizza, as one scientist memorably described it. A world of fire and sulfur, frozen in orbit around Jupiter. Neptune has a strange moon too, Triton. What makes Triton unusual is its orbit. It circles Neptune in the opposite direction to Neptune's rotation, retrograde orbit. This is highly unusual for a large moon. Almost all major moons in the solar system orbit in the same direction as their planet rotates. Triton's retrograde orbit is strong evidence that it wasn't formed in orbit around Neptune. Instead, Triton was probably a Kuiper belt object, similar to Pluto, that wandered too close to Neptune and was captured by the planet's gravity. The capture would have been a violent event. Triton's original orbit was probably highly elliptical, bringing it close to Neptune and then swinging it far out. Over time, tidal forces circularized the orbit, but at enormous cost. The energy had to go somewhere, and it went into heating Triton's interior. This heating would have melted much of Triton's interior, erasing any geological history from before its capture. Today, Triton is geologically active despite the cold. The Voyager 2 spacecraft observed geysers erupting from Triton's surface, spraying nitrogen gas and dark material several kilometers into the tenuous atmosphere. The eruptions are driven by seasonal heating, as Triton's south pole is gradually illuminated by the distant sun. Triton's eventual fate is sealed. Its retrograde orbit is slowly decaying. Tidal forces are gradually slowing Triton down and pulling it closer to Neptune. In perhaps 3.5 billion years, Triton will come within Neptune's Roche limit and be torn apart by tidal forces. The fragments will spread out to form a spectacular ring system around Neptune, far more impressive than the faint rings Neptune has today. For a while, perhaps tens of millions of years, Neptune will rival Saturn in its ring splendor. Eventually, the ring particles will spiral inward and rain down onto Neptune's atmosphere, and Triton will be gone, remembered only in the geological record of a temporary ring system. Each of these moons, Hyperion tumbling chaotically with its spongy surface, Enceladus spraying geysers into space, Io covered with active volcanoes, Triton captured from the Kuiper belt, and now slowly spiraling toward its own end, demonstrates that moons are not boring. They're not just dead rocks orbiting their planets. They're dynamic, complex worlds with their own histories and their own mysteries. Let your thoughts settle on these strange moons. Small worlds that would fit inside Texas or France. Yet they contain oceans, geysers, volcanoes, phenomena that make them some of the most interesting places in the entire solar system. They remind us that size isn't everything. Even tiny moons can be extraordinary. As we approach the end of our journey through the strange objects of the solar system, let's consider one more category of oddities. These are objects that don't fit into neat categories, things that blur the lines between different types of solar system bodies. Consider the centaurs, objects that orbit between Jupiter and Neptune, crossing the orbital paths of the giant planets. They're named after the centaurs of Greek mythology, creatures that were half horse and half human, neither one thing nor the other. Similarly, the centaur objects in our solar system are neither quite asteroids nor quite comets. They have characteristics of both. The most famous centaur is Chariklo, the largest of these objects, about 250 kilometers in diameter. In 2013, astronomers discovered something extraordinary about Chariklo. It has rings. This was the first time rings had been discovered around such a small object. Previously, only the giant planets were known to have ring systems. But Chariklo, a tiny irregular object barely larger than some moons, has two thin rings orbiting it. The rings are narrow, just a few kilometers wide, but they're dense enough to be clearly visible during stellar occultations. Another centaur, Chiron, also appears to have something similar to rings, or at least a disk of material surrounding it. Chiron is unusual in other ways too. It sometimes develops a coma, a hazy atmosphere of gas and dust like a comet, even though it's far too cold for water ice to sublimate. The activity might be driven by carbon monoxide ice or nitrogen ice, which sublimate at much lower temperatures. Chiron also varies in brightness in ways that are hard to explain, perhaps because material is occasionally ejected from its surface, creating temporary clouds of dust around it. The existence of rings around such small objects was surprising. Previously, astronomers thought you needed a large planet's gravity to maintain a stable ring system. But Chariklo, and possibly Chiron, demonstrate that rings can form around much smaller bodies. This raises intriguing questions. If small objects can have rings, how common are rings in the solar system? Might many small objects have rings we haven't detected yet? The discovery of rings around these centaurs, and later around Haumea, suggests that rings might be a common feature, at least among certain types of objects. These discoveries also have practical implications. NASA's New Horizons spacecraft is continuing into the Kuiper Belt. If it's directed to fly past another Kuiper Belt object, scientists need to know if that object might have rings. A spacecraft traveling at tens of kilometers per second could be damaged or even destroyed by impact with ring particles. The discovery of rings around Haumea made scientists more cautious. They now need to carefully check for rings around any potential flyby target. Another category of strange objects are the Trojans. These are asteroids that share a planet's orbit, sitting in stable points called Lagrange points, where the gravitational forces of the Sun and planet balance. Jupiter has thousands of Trojan asteroids clustered in two groups, one leading Jupiter in its orbit and one trailing behind. More recently, astronomers have discovered Trojans associated with other planets too. Earth has at least one Trojan asteroid, and Neptune has dozens. Even Mars has a few. The existence of Trojans is predicted by orbital mechanics, but the fact that we find them around multiple planets shows how these gravitational sweet spots can capture and hold objects over billions of years. Some of these Trojans are quite large. Jupiter's largest Trojan, Hector, is about 200 kilometers across. NASA recently launched a mission called Lucy to visit several of Jupiter's Trojans. The spacecraft will fly past 8 different Trojan asteroids over the course of its mission, giving us our first close-up views of these objects. Scientists are especially interested in the Trojans because they might be pristine samples of material from different regions of the early solar system. If they were captured early in the solar system's history, they might preserve material from the zones where the giant planets formed. Let's not forget about comets. While comets are well known, some individual comets are distinctly strange. Comet Hale-Bopp, which graced our skies in 1997, was unusual for its enormous nucleus. Most comets have nuclei only 10 to 20 kilometers across. Hale-Bopp's nucleus was estimated at 40 to 80 kilometers, making it one of the largest comets ever observed. Its great size meant it produced a spectacular display, with a bright dust tail and an even longer gas tail visible to the naked eye for months. The comet won't return until the year 4385, so Hale-Bopp's apparition was a once-in-a-lifetime event for everyone who saw it. Another strange comet is 67P Churyumov-Gerasimenko, the target of the European Space Agency's Rosetta mission. When the Rosetta spacecraft arrived at the comet in 2014, it revealed that Churyumov-Gerasimenko has a bizarre rubber duck shape with 2 distinct lobes connected by a narrow neck. High-resolution images showed the comet's surface in unprecedented detail, revealing a landscape of cliffs, boulders, pits, and smooth plains. The Rosetta mission also successfully landed a probe, called Philae on the comet's surface, the first time humans had landed on a comet. Though Philae's landing was bumpy and it ended up in a shadowed region where its solar panels couldn't charge, it still transmitted valuable data about the comet's composition and structure. The solar system is full of these oddities, objects that surprise us, that don't fit our expectations, that challenge our theories. Each one teaches us something new about the processes that shaped our cosmic neighborhood. Each one reminds us that the solar system is far more diverse and complex than we sometimes imagine. As our technology improves, as we send more spacecraft to explore distant worlds, as our telescopes become more powerful, we'll undoubtedly discover more strange objects. Perhaps we'll find more interstellar visitors passing through. Perhaps we'll discover more unusual moons or asteroids. Perhaps we'll finally find Planet 9, if it exists, lurking in the years' outer darkness. But for now, let's rest with the knowledge that our solar system, our cosmic home, is a wonderfully strange place. It contains worlds shaped like footballs and walnuts and rubber ducks. It has moons that spray geysers into space, and moons covered with active volcanoes. It has cliffs 20 kilometers high where you could fall for 10 minutes. It has rings around tiny asteroids and dwarf planets. It has visitors from other stars and objects that tumble chaotically through space. Each of these strange objects has its own story, its own history written in craters and ridges and canyons and compositions. By studying them, we're learning the story of how the solar system formed, how it evolved, how it became the place we call home. We're learning that the universe is more creative, more diverse, more surprising than we could have imagined. We're learning that even in our own celestial backyard, there are mysteries waiting to be solved and wonders waiting to be discovered. So rest now, knowing that above us, beyond the blue sky and the darkness of space, these strange worlds continue their eternal dance around the sun. Oumuamua is racing toward the stars, never to return. Haumea spins like a cosmic top, completing a rotation every 4 hours. Iapetus circles Saturn, half bright and half dark, its equatorial ridge standing like a frozen seam. Miranda tumbles in orbit around tilted Uranus, its towering cliffs and patchwork surface waiting for another visitor. Enceladus erupts geysers toward the stars, and countless other objects, known and unknown, drift through the cosmic dark. You've done enough pondering for tonight. You've journeyed from the inner solar system to the Kuiper Belt and beyond. You've visited strange moons and dwarf planets, seen landscapes unlike anything on Earth, contemplated mysteries that scientists are still working to solve. Let these images rest gently in your mind now. Don't strain to remember every detail. Just let the wonder wash over you. The simple marvel that we live in such a strange and beautiful solar system. Close your eyes now. Feel yourself sinking deeper into comfort, into rest. Let your breathing slow and deepen. The strange objects of the solar system will still be there tomorrow, continuing their ancient orbits, keeping their secrets, waiting for the next generation of explorers to visit them. But for now, let them go. Let everything go. You have done enough for today. The universe will wait. The mysteries will wait. Sleep now and dream of distant worlds, of falling gently down towering cliffs, of rings catching starlight, of ice geysers spraying into the cosmic night. Dream of a universe full of wonders, strange and beautiful beyond imagining. Good night.